Hello, welcome to our penultimate, that is second to last, virtual lecture for SCP-105, Life in the Universe. Today, we will be looking carefully at some ideas related to communicating with extraterrestrial intelligence. These are ideas that have been around for a long time. In fact, we're going to look at an event that happened in 1974 that was designed to show the promise and opportunity that human beings had in being able to communicate across interstellar distances. In class, we've already discussed some of the challenges in thinking about what an interstellar communication might look like. And we've also thought about the question as to whether there might be any extraterrestrial intelligent groups out there in the cosmos for us to have a conversation. We're going to set aside the question as to whether these extraterrestrial intelligent groups exist, and instead focus on the technology and the philosophy behind developing different ways of communicating with groups that we have never interacted with in all of our history and may share none of the ideas that we have about intelligence, society, communication, or even life itself. So I'm going to begin by sharing this presentation with you. And what we will be looking at here is a message that's called the Arecibo Message, named after a municipality in Puerto Rico, where a large radio telescope that was funded by the United States once stood. And we'll explain what happened to that radio telescope and also a little bit about the history of what's going on. So let's start off with the two scientists who were charged with coming up with this message to extraterrestrial intelligent groups. The first scientist is a famous one for his media appearances. This is Carl Sagan. Carl Sagan had a program in the 1970s that was called Cosmos, and explained a lot of ideas related to astronomy and the cosmos and our place in it. At the time he was alive, he was perhaps the most famous American astronomer. This is a title that probably is held now by Neil deGrasse Tyson, who himself has started his own Cosmos series that you can actually see on some streaming services. Carl Sagan was working with another scientist, a radio astronomer by the name of Frank Drake, pictured here. Frank Drake is perhaps most famous for writing down an equation that we are studying in this class, which tries to describe the likelihood that we will encounter extraterrestrial intelligence in some fashion or another. You'll have a homework question as well as some other discussion board posts that will deal with this idea and the various questions that surround it. But for our purposes, we're interested in thinking about these two scientists as optimists. Both of these scientists had great hope that it might be possible in their lifetimes, perhaps, to have some sort of contact with extraterrestrial intelligence. Frank Drake is still alive, but he's in his 90s. Carl Sagan passed away about 20 years ago. And so it's not at all clear that their dream will be fulfilled. But perhaps it can be passed on to the dreams of the current generation and maybe beyond. The message was sent from a telescope, which is a little bit interesting to think about. Telescopes are normally thought of as receivers of information and messages. But a radio telescope such as this can be used as either a receiver or a transmitter. And in fact, this radio telescope was designed to be able to transmit radio frequencies through space, mostly as a way to detect different things in our solar system. This is called radar ranging and is not too different from the equipment that we use to detect planes in the sky or to find the speed of cars in so-called radar guns. This is a much more powerful radio transmitter at the Arecibo radio telescope. And when they decided to recommission this telescope in 1974, they thought that it would be good to have a ceremony where they sent a message to the stars, a message that would be produced by the two scientists you just saw, coded into the devices that are used at the telescope to produce radio modulation that would then travel interstellar distances, maybe to be detected some extraterrestrial intelligence. Now, this commission happened in 1974, and the Arecibo radio telescope was operating then for the next 40 years. About 10 years ago, funding for the telescope was cut. And slowly the telescope began to deteriorate. And then, shortly before the pandemic in 2019, something disastrous happened, which is that the supporting struts that you saw that kept the equipment that could either detect or transmit radio waves crashed in to the dome of the radio telescope. This radio telescope is kilometers across, so it's gigantic. And this destruction was pretty unfortunate, to say the least. And we are still wondering whether this telescope will be rebuilt. Right now, there haven't been many ideas put forth on how to rebuild it, where to get the funding. But it is possible that this might be rebuilt. It's in a great location to be doing radio astronomy. And it, at the time, was the largest telescope in the world. Now it's been eclipsed by a similar telescope in China that's a bit larger. But if it were to be rebuilt, it would still be the second largest telescope in the world. Very, very big telescope allows you to be very sensitive to very faint radio signals across the sky. So where did they send this message to? Well, they chose a cluster of stars that happened to be directly overhead. This cluster of stars is called Messier 13. It's a globular cluster, which means that the stars in it are very tightly packed together. In fact, sending a message in this direction means that when the message arrives, its potential is that maybe hundreds of thousands or millions of stars will be in view of the message in terms of how big the beam was. Unfortunately, clusters of stars like this that are highly compact are also very old. And when they're very old, that means that they were formed at a time when there weren't a lot of heavy elements in our galaxy. Heavy elements are formed from exploding stars and from various processes that happen after the first round of star formation. And around our own part of the galaxy, there are a lot of heavy elements. And that's good because Earth, for example, is mostly heavy elements. But in this globular cluster, and indeed all globular clusters, very few heavy elements are found. That might mean there aren't many opportunities for planets around these stars to be formed, although we don't know that for certain. Another issue is that the stars are so tightly packed that the interactions between stars could disrupt planetary systems and send planets flying out of the cluster. It's not clear to astronomers that this then is the best target for sending a message. Are there intelligent life forms that live in planetary systems around stars in M13? Maybe. But one more additional problem is that Messier 13 is some 13,000 light years away, which means it's going to take this message 13,000 years to get there. So even if there is somebody waiting to receive the message, we won't find out about it till we're long gone. So why was this message sent with radio waves? Well, apart from having a radio transmitter, that's very fortunate technology, it turns out that radio is an excellent form of communication across interstellar distances. First of all, there's a wide range of possible frequencies and wavelengths that you can send radio messages. You can see that indicated here in terms of how broad the different parts of the spectrum are. You can, in fact, not even see where the visible light is in this diagram because it's such a narrow band of electromagnetic radiation. But here you can see all the possible radio waves that will transmit out into space. You can see that they take up almost as much frequency domain as the rest of the electromagnetic spectrum. This shows a little bit about how you would produce radio waves. We often take those radio waves and turn them into vibrations or sound. And so you can take sound, turn those vibrations into radio waves, then turn those radio waves back into amplified vibrations. And this is what we normally think of as radio. The radio message that was sent to M13 wasn't intended to be listened to as sound. It was intended to have a maximum amount of information for a minimum amount of signal. And we'll see how they figured out how to do that in just a bit. One thing to realize about the choice of radio waves is that radio waves are very penetrative. They will go a very long distance without interacting with many media. And you can see this where the electromagnetic spectrum penetrates the Earth's atmosphere. Most of the Earth's atmosphere will block electromagnetic waves. And this is true for a lot of the intervening material in our galaxy and beyond. But radio tends to go right through. And that's an important feature that radio has, its transmissibility. So what did they send? Well, I'm showing what they sent right now. Really what they sent were bursts of radio waves. And these bursts were modulated at different frequencies, sometimes a lower frequency, sometimes a higher frequency. And then there was a gap, and then they would burst another amount of radio waves out in that direction of M13, either at the high or the low frequency. And they kept track of this. And when they did a low frequency burst, we put a 0 on this. And when they did a high frequency burst, we put a 1. And they did it over and over and over again until they came to an ending point, which might not seem clear to you or me, but was chosen very deliberately. And the order and the manner in which they sent this was all very deliberate. They wanted to send the low bursts that they did and the high bursts that they did in order to encode a message. Now, this is a message you probably cannot see just by looking at this diagram. So we'll have to investigate a little bit more carefully about how to decode this message. The first thing we need to understand to decode the message is the question of prime numbers. Prime numbers are very interesting things to think about because a number that is prime everywhere in the universe. It's not just prime here on Earth, but it is a prime number no matter where mathematics is true. And as far as we can tell, mathematics is true everywhere. What you're seeing here is an animation on how to generate the prime numbers. And this generation of prime numbers happens in a way to produce very particular and unique series of things that are very useful for calculation. 2, 3, 5, 7, 11, 13, 17, 19, and so on. Now imagine that you received a message from somebody and it indicated that there was a prime number somewhere in that message. You might come to understand that this would have been created by some sort of intelligent being that understood what a prime number was. And since prime numbers are the same, regardless of how you count, regardless of what numbering system is used, this means that very likely someone that has the technology to receive radio waves also is aware of prime numbers. This was the thought, that the intelligent groups that we're trying to communicate with will know about prime numbers. So how did they use prime numbers? Well, one thing you can do with prime numbers is you can multiply them together. If I take 2 prime numbers and I multiply them together, I get something called a semi-prime number. And what makes a semi-prime number interesting is that there's only one way to divide it into 2 parts. In other words, if you have 2 numbers that are multiplied by each other and they equal a semi-prime, there's only 2 ways that you can have those numbers multiply by each other to get those semi-primes. So let's take the first example, the number 4. 2 is a prime number, and I can multiply 2 by 2 to get 4. What about 6? Well, 6, I can multiply 2 times 3, or I can multiply 3 times 2 to get 6. But there's no other combination of numbers that I can put together to create 6. 6 is a semi-prime number because it has only 2 factors that are prime. This is the list of semi-prime numbers. The red ones are even, which means that one of their factors is 2 and the other factor is another prime number. We've come to understand that this isn't particularly useful for what we're trying to do. The prime numbers that are multiples of themselves, 4, 9, 25, 49, the semi-prime numbers that are actually square numbers, 2 prime numbers multiplied together, are listed in bold in this image. And then all of the black numbers are semi-prime numbers that have factors of 3 or greater and that are different from each other. When we looked at that message, we might not have been able to tell there was a message involved. And perhaps that's because we weren't trying to look for an image. But it is possible to use those ones and zeros to create an image, which is what the Arecibo message is trying to do. So for example, we might say that the number 1 stands for a darkened in pixel. We might say the number 0 stands in for a light pixel. And we alternate dark and light depending on whether we see ones and zeros. We're going to try to arrange an image in a grid. And since we're going to have a semi-prime number of bits, that grid is going to be arranged in a fashion so that I have a prime number on one side and a prime number on the other side. And this is exactly how the Arecibo message was sent. A semi-prime number of digits was sent out as the message. And then that message can only be created in an image by putting the 2 prime numbers that are factors of that semi-prime number as the length and the width of the image. So when you do this with the 1,679 ones and zeros that were sent out, you find that the factors of this semi-prime are 73 and 23. Great. So let's do 73 columns and 23 rows. And you do that and you come up with this message, which doesn't look like much of anything. You can ignore the colors here. We'll actually show what the colors are in a bit. But the important thing to note here is that there is no seeming image that you can make out using this 73 by 23 image. But this isn't the only way to arrange 1,679 pixels into its semi-prime prime number factor image. The other way to do it is to have 23 columns and 73 rows. And if you do that, you do this. This looks much more like a message. And indeed, this was the message that Drake and Sagan intended on sending out into the cosmos. The colors here are just to draw your eye towards different sections that Drake and Sagan had chosen to include in their message. So the top white column is one part of the message, the next purple columns are, so the top white rows are one part of the message, the purple rows are another part of the message, the green another, and so on. Let's describe each of these parts of the message so that you know what they decided to do. The first thing they did was list all the numbers 1 through 10. Since we use a base 10 numbering system in most of the world, they thought that was a reasonable thing to send. Now you might not recognize it as base 10, but in fact it is. It's just written slightly differently. It's written in binary. This is how you write the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in binary. And if you look at what the color coding for this would look like, and you look at what those top few rows of the Arecibo message look like, you will see that this is the numbers 1 through 10. The next row in purple is actually an indication of the important atoms for life. The way these atoms were determined is by the number of protons in the nucleus. And in fact, the atoms that were chosen were the atoms C, H, O, and N, except the order was H, C, O, H, C, N, and O in order. How do we know that these are the atoms? Well, it's hard to know, but the numbers that were chosen correspond to the numbers up above. The numbers are 1, 6, 7, and 8, which corresponds to the atomic numbers for hydrogen, carbon, nitrogen, and oxygen. Now, why not phosphorus and sulfur? It's a good question. They didn't think to include phosphorus and sulfur. They perhaps didn't have enough space to think about those. But here we have some of the most important atoms represented in this message, minus the P and the S. The next two things that are shown are indications of DNA. And what you see in green, first of all, is a way of taking the atoms that were indicated up above, the C, H, O, and N, and putting them together to create the base pairs of DNA. Now, because they didn't include phosphorus, they had no way of including the phosphorus backbone. But they thought that the base pairs were important enough. So these are ways of chemically indicating the base pairs, at least the number of atoms of each that are included in each of the base pairs and how they're arranged. And then you can see below that the double helix. The two blue lines are supposed to indicate the approximate shape of the DNA double helix, whereas the white band in the middle is actually a number which corresponds to the approximate number of DNA base pairs in the human genome, at least as was known in 1974. Since then, we've revised that number upward somewhat. And so the message is actually somewhat inaccurate. So you should get the sense that what they were trying to do was communicate this information. Now, if they were able to do that successfully or not, it's not something that I'm quite aware of myself. It's hard for me to judge. But they certainly have the information there. The carbon, hydrogen, oxygen, and nitrogen, that's important, but the phosphorus was omitted, the stuff that's on the outside in this diagram. Of course, below the DNA, you see an indication of a human being. And then there is an attempt to indicate how tall the human being is, which is done by assuming that the people know what the wavelength of the radio message is, and then multiply that by the number that they have there to get the human height. Might be successful, might not be. That's what is indicated on the left. On the right is what's indicated as is the population of the Earth in 1974. You can see it was about 4 billion. So if the message was sent today, it would have to be closer to 7.5 billion, almost 8 billion. Finally, below the human being, you can see some interesting dots that are indicating the solar system. The sun is on the left, and then we have the 4 inner planets, the 4 outer planets, and then another little dot all the way on the right. That dot is Pluto. At the time, people considered it part of the solar system as one of 9 planets, and now it has been demoted to something less than a planet. And so if you were going to be making the Arecibo message today, you might want to incorporate that new understanding of how many planets there are in our solar system. Yeah. Otherwise, it might get a little confusing. Finally, at the bottom, you can see a mock-up of the Arecibo Space Telescope itself. Perhaps not the best drawing in the world, but something that looks a little bit like what they sent this message from. And at the very bottom is a measurement of approximately what the size of the Arecibo Space Telescope is. And that's the entire message. A lot of information in there. Some of it might be things that could be interpreted. Some of it might be difficult to interpret. But nevertheless, that's how the message was sent. Now, being able to send messages like this is something that we are still capable of today. I'm going to have you create your own Arecibo message. You will do this by producing a grid that is a semiprime number of pixels. And you'll have to choose a grid that's at least 100. So one of the numbers that you'll have to choose will be bigger than the semiprime. The number of pixels you have to choose will be bigger than 100. And you'll want to choose some message. You can choose any message you'd like. But once you do that, you will be submitting it to a web app, which will try to interpret it. And this web app has been coded up to try to look at any message that's a string of ones and zeros and see if it can't create one of these images, one of these Arecibo message type images. And if it can, it shows you what it thinks the image is, and you can see whether you were successful in sending your image or not. So that will be our final lab for SCP-105. We don't have an answer to the question as to whether there is any life beyond the Earth yet, nor do we have an answer to this question of whether there might be intelligent life able to receive this Arecibo message. But we can still keep looking, we can still keep trying. I think that's the big message that we have for this class, is trying to be as careful as we can in observing and seeing if there might be some possibilities out there that might show us something unexpected or amazing as we look for life in the universe. Thanks very much, and I'll see you one more time.